Hello guys, welcome back. So here we have another question on communication systems from GATE 2021. The autocorrelation function Rx of tau of a wide-sense stationary random process x of t is shown in the figure. So Rx of tau is given and the average power of x of t is dash. So first we need to understand what is wide-sense stationary signal. So first thing to understand is it is not a deterministic signal. So you cannot represent it mathematically like a sine omega t or u of t, something like that. So it is not a deterministic signal. So what is it? It is a random signal, right? And usually it can be represented by a random process x as a function of time, right? So this is for any random process, but for wide sense stationary signal we have two properties. One is that your mean and covariance is independent of time. So your mean mu of t, mu x of t, which is nothing but expectation of your x of t, should be a constant, and your autocorrelation function, which is your covariance, right? So your Rx of t1 comma t2, this is nothing but expectation of x of t1 into x of t2 itself is only the function of the difference t1 minus t2. It doesn't directly depend on where that t1 and t2 is positioned, but it is only a function of its difference. So this you can call it as tau, and then you can write it as expectation of x of t into x of t plus tau. So now this is what they have given, this Rx of t. Rx of tau is expectation of x of t into x of t plus tau. So this is nothing but your calculation of your autocorrelation function when probability distribution of x of t is given. But if you have the signal x of t, which is time, right, then how will you calculate Rx of tau? So for a power signal, your Rx of tau is nothing but limit t tending to infinity 1 over t integral minus t by 2 to t by 2 x of t into x of t plus tau into dt. So this is your same expectation but in your time domain equivalent. Okay. So now they're asking us to calculate the average power. So for x of t, what do you think is the average power? So power formula, right? Is nothing but you integrate over one time period x of t square into dt. Then you take the average and then you tend your limit t to infinity. So can you make the comparisons between these two formulas? When is your average power equal to px of tau, rx of tau? When tau is equal to 0, right? So your p average is nothing but your autocorrelation function evaluated at tau equal to 0. So it is very straightforward here, which is nothing but your value 2. If you also want to visualize it in the frequency domain form, your Rx of tau is nothing but limit t tends to infinity 1 over t, and this anyway you can tend to infinity, right? So in that case it becomes your x of t convolved with x of minus t, right? So this in your frequency domain, if you take a Fourier transform, this is nothing but limit t tends to infinity 1 over t, this is x of f, and this is x conjugate of f. So this is equal to limit t tends to infinity 1 over t mod x of f whole square. And since this integral, if we are limiting to minus t by 2 to t by 2, we can put this as t here. So this becomes t, and this itself is nothing but your power spectral density of x. Power spectral density. So your xx of f is nothing but your Fourier transform of your Rx of tau. So this integral minus infinity to infinity Rx of t e power minus 2 pi j 2 pi ft into dt. Or the other way around, your Rx of tau is integral minus infinity to infinity xx of f e power j 2 pi f tau df. So now you want the power spectral density, total power, right? Average power. So P average is nothing but your total power. So Xx of F into dF. So this is nothing but your Rx evaluated at 0 again. So even in terms of power spectral density, it again comes back to your Rx of 0. So the answer to this is